So the last class we just started talking about the square design, which is what we call it as Latin square design, where we are talking about 3 variables. Mind you, so far we have not talked about interactions, okay. We will do interactions after this, okay. We will start with interactions slowly, but this is the idea to include as many independent components as possible. These are independent variables, right. So we have 3 independent entities here, the rows, columns and the entries itself, but now the issue is it has to be in a square design, okay. That is why it is a Latin square. If it is not in a square design, then repetitions will occur and you will not be able to do disentangle them, okay. So that is why each entry, so if you go wise, row wise, column wise or entry wise, all of them will have one element in each row, column or entry. So what I mean is, if you look at column A, B, C, D, E, there is no repetition and there is an exact match, and there are 5 treatments and those 5 entries are there, there is no 6th. Same way row, same along column, okay. So this is a square design, and this square could keep increasing. You could have a 4 cross 4, 5 cross 5, 6 cross 6, etc. okay. So you can, so the idea behind is, usually when you assume independence, you assume that they are independent nuisance factors, or it could be also independent treatment factors. So in general it takes care of 3 things, 3 variables into account, 3 independent factors into account, factors or variables or treatments or nuisance, etc. into account, okay. So the Latin square model again is, now I have mu, which is a constant, now I have alpha I, tau j, beta k plus epsilon I j k, okay. 3 entries here, rows, columns, entries itself, that is treatments, blocking and one more blocking, if you want to call it that way, okay. So this is the statistical model for a Latin square, where we have extended by one more independent variable, and then the sum square total is now split into row, columns and then treatments and sum squared error. Again the advantage of doing it is, sum square error becomes even lower, but at the same time the degrees of freedom also gets lower, okay. Nothing comes for free, so the degrees of freedoms also gets lower, okay. So this is what we have, sum square row plus columns plus treatments plus error. Now we are not going to derive things, okay. It will, as you know, the complications have built up. So the way we dealt with ANOVA is not the way we dealt with RCBD. RCBD I did not differentiate, I used the rules of least squares to write the equations. Here I am going to directly write the equations. How many equations will I have? How many equations will I have? Now it is a square design, which is interesting, right. So all are A, there is no A plus B kind of thing, there is no. So if you call it as P, you have how many equations? 3p plus 1 equations, right, 3p plus 1 equations, P for rows, P for columns and P for entries. So 3p parameters, so 3p plus 1, and that will also depend on the square design itself. If you take a 4 cross 1, it is going to be 13, 5 cross 5 it is going to be 16, etc. The P is the Latin square itself, the square number is the P. So you have 3p plus 1 equations, okay, and your F statistic is going to be again mean square treatment by mean squared error, okay. Now again you could have total degrees of freedom is how much? Total degrees of freedom, total, the grand sum. So you have 5, if the square design is 5, the total data points is 5 square, 25 minus 1 the grand mean mu. So 24 degrees of freedom you have. So you can split it into p minus 1 plus p minus 1 rows, columns and treatments, and this naturally falls out, okay. So p squared minus 1 minus p minus 1 minus p minus 1 minus, sorry, equals to degrees of freedom of sum squared error. which is equal to p minus 2 into p minus 1. You understand how did I get p minus 2 into p minus 1? Total degrees of freedom is p squared minus 1, and what do I have for rows? It is p minus 1, columns p minus 1, treatments p minus 1. So, p squared minus 1 minus p minus 1 minus p minus 1 minus p minus 1 should give you the sum squared error degrees of freedom. Okay. This you can calculate it. Okay. So, that is nothing but p minus 2 into p minus 1. So, that is the degrees of freedom for error. Okay. Now, notice this will be lower than what? Your RCBD. This is definitely lower than your RCBD. Okay. Any questions so far? Does it make sense? This only one p, the square element has to be chosen. If you choose the p, everything is fixed. So, now we have F test again, mean square treatment over mean squared error. Okay. Keep that in mind, all of them runs under the assumption of Gaussianity so far. Okay, we have not moved out of Gaussianity for instance. So, this is the total block diagram of, or the diagram for the table for Latin square, treatments, rows, columns. So, again this can be derived, but now we are not deriving any of this. Okay, I am not going to derive any of this because we have done for ANOVA in detail, RCBD I use the rules to derive it, now I am not deriving anything here. Okay. So, it will be the same lines as ANOVA or RCBD. If you look at the formulas, everything will be similar except degrees of freedom would have changed. Now, if it is a 4 by 4 Latin square, what is the degree of freedom of treatments? It is just 3, pathetic, right? Very small, yes or no? If I have a 4 cross 4 Latin square, then I have only 3 degrees of freedom for treatment, 3 degrees of freedom for rows, columns, and what about degrees of freedom for error? P minus 2 into P minus 1, which will be 3 minus, so if I 4 minus 2, 2 into 1, 2 into 2, 2 into 3, 6, very less totally. All of them become very, very small, right? It is nothing, nowhere close to 30, it is on the extremely lower side if you are doing a 4 cross 4 Latin square, right. So, how do we improve? So, the problem clearly in this is, see, the formulas will be exactly ditto of what you did in RCBD and your ANOVA, you can easily derive this. Okay. It is in fact, if you look at, we just replaced with dot 3 dots instead of 2, that is all I did, nothing much here. Okay. But what is interesting here is the problem is your degrees of freedom goes down drastically. In RCBD and ANOVA I had the luxury of either having more rows or more columns, here I do not have any of that, it is a square design. Okay. So, how do we improve the degrees of freedom? How do I improve the degrees of freedom? Because the degrees of freedom is so low. So, when you have this degrees of freedom to be lower, look at your confidence limit, it will be wider, because you look at t square distribution values, you will know that. So, your every thing gets affected. If your degrees of freedom gets lower and lower, it becomes the bounds become larger. Okay. So, you will not be able to prove or disprove things at a finer detail. Okay. So, n sigma squared over n always plays a role, right. So, this degrees of freedom is important and it should be higher. Now, you can only use t distribution and t distribution also on the lower side, right. I mean sorry, f distribution also on the lower side, it will be like 2 degrees of, you will not go to 30 or 40 degrees of freedom, you are just doing it 3 degrees of freedom, very less. So, how do I improve this? How do we improve the degrees of freedom? How do I do more? It is Latin square. How do I do more? It is a Latin square design. You are not going to improve the degrees of freedom. If you have only very few data points left to say, what can you say? Right? So your experimental size is what? 4 cross 4, you are doing only 16 experiments. That is on the lower side. And in 16 experiments, what do you want to do? You want to talk about 3 factors, which is your treatment, rows, columns, and then you want to say whether treatment is better or not. Very high ambitious, right? With just a 16 experiments if it is a 4 cross 4, right? So that is where the problem is. One of the ways to do is what? To improve, or the only way, the easiest way to do is replicate a Latin square. You conduct the Latin square experiment, but multiple times. So now you are replicating the square itself. That is what we do. So you have done 16 experiments, then next conduct another 16 square, right. So those are ways in which you can actually improve your degrees of freedom. Now how does the degrees of freedom get improved? If you talk about it, so the total number of data points is what? So the total is going to be n p squared minus 1. So you have conducted n blocks, so this is going to be n into n p squared minus 1. Remember, the overall mean is only 1 you are going to collect, you are going to conduct many squares and then merge them. So the total is n into p squared, n p squared minus 1. Instead of p squared, now if you do it 5 times, 5 p squared minus 1, 5 replications. Now the total degrees of freedom would have increased, okay. And now one of the things when you replicate, you have to keep in mind is there will also be a, when you replicate you cannot do a exact replication, there will be variations in when you replicate itself, right, yes or no. When you are making same unit, I mean if a company is making balls, tennis balls, is all the tennis balls same? Plastic chairs, it is just a mold, but even in the mold, do you think everything looks same, exactly will be same? No, there will be variations, right, the way it is molded. So even when you replicate, there will be variations due to replications, that has to be captured. So you have what is known as a replicate sum squared. You see what I mean? When you replicate, you have to think about how to capture replication aspects. So that is where we talk about replicate sum squares. So this is your row treatment, rows, columns. Remember, these degrees of freedom does not change, because p minus 1 is the degrees of freedom. If there are A treatments, A minus 1 is the degrees of freedom for treatment. Similarly for rows and columns. What will change if you change n, if you do more replications, what will change? What will change? Which degrees of freedom will go high? When you, yes, error degrees of freedom will go high, right. That is what we want. We cannot change the degrees of freedom of rows, columns or treatments, because it is fixed. If you do p treatments, the grand mean of treatment is 1, so p minus 1 is the degrees of freedom for treatment, no change in it. But ideally what do you want the treatment, what do you want to be higher is the degrees of freedom for error, because we are taking a ratio and degrees of freedoms of error makes a big impact. So you want to increase the degrees of freedom of error, sum squared error or mean squared error, that can be increased by replications. So when you replicate, everything remains the same, it is going to be p minus 1, p minus 1, p minus 1, right, because it is the Latin square design, so it is p, okay. But what is changing is the total degrees of freedom have increased, it has increased from p squared minus 1 to the square p squared minus 1 to n times. So the total data point is n p squared and only one grand mean, so the degrees of freedom is NP squared minus 1. So notice this is where the change is, and this will affect what? This will affect your error degrees of freedom. And how do I get error degrees of freedom? Simple, NP square minus 1 minus 3p minus 1. This is nothing but, how did I get this? Is nothing but NP squared minus 1 minus degrees of freedom for sum squared error. Got it? So you have replicates. So when you replicate the square, meaning you have conducted first 16 experiments, now you have to conduct the second 16 experiments. Obviously there is a variation due to replication, that has to be accounted for. Okay. So there is a replication squared as well. So now I will have, what do I have? I have 4 indices, not just 3, IJK, I will have IJKL, 4 indices, rows, treatments, columns, replicates. Okay. So you look at the formula, that will be always the same, yi square minus y triple, the grand mean is y 4 dot square divided by n. Okay. And for replicates it will be triple dot L square, where L is the replicate index, I is treatment, sorry, I is the row, I is indices row, J is J I have noted here as treatment, K as column, L as replicates. So you have 4 indices. When you replicate, this has to be kept in mind, the replicate variation also has to be accounted for. That is why you will have 4 indices, I for rows, K, J, here I have taken for treatment, K for columns and L for replicates. And if you look at, there is a standard pattern in the formula. Now you should have observed, this is y dot, so this is treatment, treatment indices is J, y sum along everything except for J, so y dot J dot square divided by total data points NP, and y I dot square divided by NP, and then y dot K dot square divided by NP. Okay. This is for standard for treatment rows and columns. For replicates there are only 1 over p squared. So for replicates alone the formula will vary. Why? Because the number of data points in a replicate is only p squared. So you have 1 over p square times y square minus y grand sum square divided by n. This formula if you look at, it will be exactly same like your ANOVA and RCBD. So now you have to start relating. Okay. So look at ANOVA RCBD, how you have derived, it will be the same way, now just that the indices have increased. Okay. So now we are talking about rows, columns, replicates and your treatments. Okay. Replicates you do not do NP, you have only in one replicate you have 1 by p square data points. So total number of data points is p square in a replicate. Okay. Clear? Any questions so far? You understand this table? So this is the way when I start doing replications of Latin square. Okay. So people generally when they start doing this, they will start, if they think of independent sources, then they will start doing Latin square. Okay. But now these are in fact even less standard. So today people talk about 2 factorial, n factorial experiments and so on. So we will move on to that, where interactions are taken into account. Okay. So far we have not learned any interactions, we have learned one way ANOVA without interactions. Okay. That is why it is called one way ANOVA, only one factor. I did not consider 2 factors. If you consider 2 factor, it will become a 2-way ANOVA, and also I should consider interactions. Okay. Now we have learned one way ANOVA, then built on one way ANOVA to learn blocking for multiple variables, that is what Latin square is. Okay. Clear? Any questions? I have given a little bit of derivation, I will not do this. Okay. So this is replication of this thing. Okay. So when you replicate, you have to keep in mind, okay, the batches and operators, or the variable should be as close to the as original as possible. Okay. Even then there will be replication issues, When you start changing things, then it is no longer a replication. You understand what do I mean by replication? It should be same, okay. If you do differently, then what will happen? Your replicate will, what will happen? Your replicate sum squared will start increasing, okay. So you have to keep in mind as close as possible. You can keep rows and columns the same and do it. You can keep the rows same, columns different. You can change both and do it, but when you change both and do the replications, what will happen? If you do not care about rows and columns, but only worry about treatments and leave rows and columns take its own path, what will happen? Your replicate sum squared error is going to increase, go up. That has to be considered, okay. So each of these cases we have something, okay. So this is ideal case where everything is replicated properly, where everything is replicated exactly, meaning you have rows, columns, treatments, exact replication. This is case 1. Now I have one of them replicated properly, the other one does not replicate properly. In this case, can you tell me which is replicated and which is not replicated properly? Rows are replicated properly, rows are not replicated, columns are replicated properly. You look at the degrees of freedoms of rows, everything remains the same. That one which is not replicated, your 2 changes, it should be NP if it is exactly replicated. You have not exactly replicated it, so what will happen? You have to consider only within that particular block, and the degrees of freedom will go higher because you have not replicated. So it is not p minus 1 exactly, because you have not replicated properly, it is n times p minus 1, because p minus 1 for each block and you have not replicated properly. So what will happen? It will be n into p minus 1. See, I have kept rows constant, columns constant, treatments constant, and I do this experiment once and I do the same time experiment second time, then it is an exact replica. Now what can I do? For whatever reasons I do not have a control over rows, I have only control over columns and treatments. You are doing human experiments, suppose one person leaves, you wanted to replicate the experiment but that person has left, what will you do? You cannot do anything about it, you have to replace it with a newer person. Now what will happen? You are not exactly replicating, right. I do with a small human study with a small population, now they are not available, now I have to conduct with a different sample. Now although my treatment can be the dosage, everything can be same, even age group can be same, but what has changed? Person have changed. So I have not replicated exactly. So when you do replicate experiments, you have to be, that is where these are the, that is why I said this will be totally new for you guys. When you conduct experiment, these are the things, this is what design of experiment is. You have to start paying attention how data is achieved, what is the degrees, how, what can you prove, etc. All of them comes when you start conducting experiments. So that is why I asked you a question, we are getting deeper into design of experiments itself, how to conduct experiments, okay. When you do this, you have to be very clear. So the ANOVA is the simplest, but ANOVA never happens. Although in papers you will see ANOVA is what you do not want, is the simplest of all. What will happen? You will have more factors and there will be factors that need to be blocked. Then RCBD, if there are multiple, then you come to Latin square. Anywhere you will be able to, you need to replicate, okay. When you start replicating, this is not just true for Latin square, I can do replication in RCBD also. RCBD also I can do replications. Now when you replicate the experiment, let us say you did this month and 1 month later you are doing another experiment. Ideally you would want everything to be exactly kept the same, but that is not going to happen. So you may keep everything same, which is nice, in that case the degrees of freedom of error is larger. But if you cannot replicate for whatever reason, if you can replicate only one, either rows or columns, in this case rows are not replicated, what happens? The degrees of freedom of error dips, because the degrees of freedom of treatment increases to n into p minus 1, because p minus 1 is not the degrees of freedom. For each block, each replication, it is p minus 1. Totally there are n into p minus 1, because you have not replicated the rows exactly. You have replicated the columns exactly, therefore for others you have p minus 1, but you have not replicated the rows exactly for whatever reason. Let us say rows are no operators or humans samples, you will not able to do the experiments on the same person, then it has changed. Okay. Now there is a case where I would have not been able to replicate both rows and columns. I do not have a control on both the nuisance factors. Imagine my treatment dosage is the same, but the material, the batch based on which this drug is made is different from the other batch. Remember, batch to batch variation exists, right? Of course, your batch of medicine could be good or not the same. When you are testing, you have to account for batch to batch variation. Suppose Pfizer is testing in one batch and testing, the idea is to test the dosage levels. Batch is a nuisance. I would ideally want it to be done for using the same batch. Now for whatever reason the batch is over, now get a different batch, same dosage levels, the treatments are the same, but both the human subjects and the batches have changed. Now you could not keep both rows and columns as constant. Again what will happen? The degrees of freedom of error is going to go down, right, because now you will have for both treatment and rows and columns it will be n into p minus 1. Okay. So these are the three cases of replication. When you replicate itself, you can do three ways. Okay. In this case, if the number of variables increases, then the number of strategies in which you can replicate also becomes complex. In this case it is easier, either rows or columns. If I do 3, then that becomes a combination. You understand? If I do 3 factors, nuisance factors, suppose you have 4 factors, then replication treatments plus 3 nuisance factors, then the replication becomes quite complex. Okay. You can keep one constant, 2 others varying, 2 constant, 1 varying, all 6 factors will come, 3 C2 combinations will come. Okay. Here it is a simple Latin square where there are only 2 nuisance factors. So it becomes a A or A, B, C, either you replicate exactly or you do not replicate one of them or both of them, clear. So that is where these 3 kinds of replications become important when you do a design of experiments, when you do a design. This is what is called as Latin square with replications. So 3 kinds of replications, clear. See, you should be thorough with ANOVA and RCBD to start following this. If you are not thorough, it will look actually truly Latin to you. Okay. Now you have to start catching up, you should be able to know RCBD so that this can be followed easily. Okay.